Two tugboats pull a disabled supertanker. Each tug exerts a constant force of 2.1 times 10 to the 6 newtons. One pulls at an angle 25 degrees west of north, the other at an angle 25 degrees east of north, and they pull the tanker a distance of 500 meters towards the north. What is the total work done by the two tugboats on the super tanker? This is the direction of motion. It is to the north. And the two forces exerted on it, one of them is 25 degrees to the east of north, the other one is 25 degrees to the west of north. Both of these are the same angle, and they both have the same force, 2.1 times 10 to the 6th newtons, 2.1 times 10 to the 6th newtons. The total work done by the two tugboats is going to be a function of the equation. Work is force times distance times cosine theta, where cosine theta, or theta, is the angle between the force and the direction of motion. In this case, the angle for both of these is the same. It's 25 degrees over here, 25 degrees over here, which means that the total work done is going to be the work done by this force and the work done by that force. Since the forces are the same and the angles are the same, it's just going to be the work of a single one multiplied by 2. So we're going to say work equals 2 times 2.1 times 10 to the 6th times 500, which is our delta x, that is how much the boat has moved, times cosine of 25. Take out a calculator, and you do 2 times 2.1 times 10 to the, times 10 to the 6th times 500, times 500 times cosine 25, making sure we are in degrees, and you get 1.9 times 10 to the 9th, which is going to be our answer, 1.9 times 10 to the 9th joules. Let's check and see if that is indeed the right answer. It is. And I'm going to set up an answer key nearby so you don't have to scroll through that every single time. What is the minimum energy needed to change the speed of a 16 kilogram car from 15 meters per second to 40 meters per second? So the minimum energy needed to change the speed of that car is the minimum energy required to add whatever the change in kinetic energy is. So in order to find out how much energy we need to figure out how much energy are we adding. And in order to do that, we are going to use the equation for kinetic energy, which is Ke is 1/2 mv squared. So initially, the car, it has 1/2 1600 times 15 squared joules of energy. Afterwards, it has 1/2 1600 times 40 squared joules of energy, which means initially its kinetic energy is 0.5 times 1600 times 15 squared, and that is 180,000. And then afterwards, all we're going to do is we're going to change this 15 to a 40. And when we do so, we get 1,280,000 joules of energy. And now, in order to figure out how much energy we need to provide, we take our answer and we subtract the original number, which was 180,000, and we get our final answer, which is delta Ke is going to be 1,100,000 joules. Let us see if that is in fact the correct answer. It is, in fact, the correct answer. Moving on. Concrete block is pulled 3 meters across a frictionless surface by a 65 Newton force. The net work done on the block is 120 joules. What angle does the rope make with the horizontal? Again, we're using the equation from question 1. Work equals force times delta x times cosine theta. Here we are given the total work. We are given the delta x, and we are given the force. All we need to do is solve for theta. 120 equals 65 times 3 times cosine theta. So we do 120 divided by 65 times 3. 120 divided by 65 times 3. We have cosine theta equals 0.615. In order to solve for theta, we always use an inverse trig function. So we go to our thing over here, we go to function, we go to cosine -1 of point, and we'll just go with answer because that's the safest way. We have, our answer is theta equals 52 degrees. That is indeed the correct answer. That is the answer to question 3. A sled having a certain initial speed on a horizontal surface comes to rest after traveling 10 meters. If the coefficient of kinetic friction between the object and the surface is 0.2, what is the initial speed of the object? It looks like this is a friction question. I'm going to assume that it is indeed a friction question, in which case you're not responsible for it. Congratulations. As shown in the figure below, a box of mass m equals 68 kilograms. Initially at rest is pushed at a distance across a rough warehouse floor by an applied force F of A. Across a rough warehouse. Okay, fine. Directed at an angle of 30 degrees below the horizontal. The kinetic friction force between the floor and the box is 90 newtons. Determine the following. Work done by the applied force. Work done by the force of gravity. Work done by the normal force. Work done by the force of friction. Calculate the net work on the box. The speed of the block at the end of the rough surface. So, work done by the applied force, let's do these in succession, is going to be the force of the applied force is 214, and then distance is, for all of these, is 61. That is not a 6. Distance is 61, and then the angle is 30 degrees, cosine of 30. And you spit this all into a calculator, and it spits back at you 214 times 61 times cosine 30. That number, 11,305. Part B is really simple. The work done by the force of gravity is 0. Force of gravity is directed down. It is not helping nor hurting this motion. It is perpendicular to it. If you want to get technical, the reason why this ends up being 0 is because cosine becomes 90 and cosine of 90 is 0. So therefore we're good. For the similar reasons, the normal force, the work done by the normal force, is also going to be 0. The normal force is directed up, which is at a 90-degree angle to our direction of motion, which is to the right. The work done by the normal force, by the force of friction, is the force of friction is directed opposite the direction of motion. So we are going to do 90, which is our force of friction, times 61, times cosine of 180, because this is an 180-degree angle. Or you could just remember that the force of friction is just going to be negative, because cosine of 180 is just -1. And we do 90 times 61. And we either take this and we just make it negative, or we do cosine of 180 for thoroughness, and we get -5,490. Negative over there. Let's make sure to keep that straight. The net work done on the box is going to be the sum of A, B, C, and D, which is just really going to be A minus D. So we go back to our calculator and we do this guy, 11,305 plus the answer, which is 5,815. That is the net work done on the box. It's this plus this. It's 11,305 minus 5,490, which is 5,815. Apologies. And since that is the net work done on the box, we can use the net work done on the box to calculate the speed of the block at the end of the rough surface. The reason why this is helpful is because the work equals the change in energy. So that means that after 5,815 joules were done, the energy has been changed by that much. Initially, its kinetic energy is going to be 0 because it is initially at rest, which means that afterwards its kinetic energy is going to be 5815. We can use that fact to calculate its speed because Ke equals 1/2 mv squared. If after this its kinetic energy, its total kinetic energy is 5815 greater than it began, and it began at 0, that means that its kinetic energy is going to be 5815 at the end of this whole journey, which means that we can write 5815 equals 1/2 times the mass, which is given to us up here. It is 68. So 1/2 times 68 times v squared. You then multiply both sides by 2 and then divide by 68. So let's go over here. We have answer times 2 divided by 68 gives us that 171 equals v squared. So we take the square root of that answer to give us our final answer, which is v equals 13 meters per second, which is going to be our final answer. Moving on. 2 times 10 to the negative third kilogram bead. It's a very light bead. I guess beads are light, so that makes sense. Slides along a frictionless wire as shown in the figure at point A. The bead is moving to the right with a speed of 2 meters per second. What is the potential energy of the bead at point A? Potential energy is, let's just start by making sure that we're in the right units. We can see that our mass is in kilograms, but our heights need to be in meters. So instead of 100 centimeters, we're just going to write 1 meter. Instead of 80 centimeters, we're just going to write 0.8 meters, just for simplicity. Potential energy of the bead at point A is going to be m times g times h. So which is going to be 2 times 10 to the negative 3 times 9.8 times 1, which is just going to equal 1.96 times 10 to the negative 2. Yeah, 2 times 10 to the negative 2, same business. That amount of joules. What is the kinetic energy of the bead at point A? So we are told that at point A, the bead is moving to the right with a speed of 2 meters per second. We can use that to calculate its kinetic energy. So that is just Ke equals 1/2 mv squared equals 1/2 2 times 10 to the negative third times 2 squared, which is 4, multiplied by 2, divided by 2 gets you 2 times 2 is 4. So after all of that, we're just back to 4 times 10 to the negative third is our kinetic energy. 4 times 10 to the negative 3 is our kinetic energy. Moving on from there. So what is the kinetic energy of the bead at point B? So the kinetic energy at point B is going to be whatever kinetic energy the bead had at point A, plus all of the potential energy that it lost by moving from A to B. The simpler way of thinking about this is, meaning the way that works for all scenarios, is that we are always going to say that Ke initial plus Pe initial equals Ke final plus Pe final. So our initial point is point A and our final point is point B, and we care about the kinetic energy at point B. So we are looking to solve for this guy over here. And thankfully, we have some help because we can see clearly that the potential energy at point B is 0. That is this height over here. And we know that the initial kinetic energy, the kinetic energy at point A, we have from parts 1 and 2. So the kinetic energy at point A is 4 times 10 to the negative third. The potential energy at part A is 2 times 10 to the negative 2. And that is going to equal KEF, so we can just solve very quickly. 4 times 10 to the negative third plus 2 times 10 to the negative 2 is just 2.4. KEF equals 2.4 times 10 to the negative 2. That is indeed the correct answer. That is part C. What is the speed of the ball at point B? So now that we have the kinetic energy, we can calculate the speed. Let's just separate all of these into nice little separate little things. This is going to become D. So the speed of the pole of point B is going to be 1/2 mv squared of the KE. So 2.4 times 10 to the negative 2 equals 1/2. The mass is 2 times 10 to the negative 3 times v squared. And then you solve for v. So you multiply both sides by 2. You get 4.8 times 10 to the negative 2. Let's just use a calculator because that is much simpler. 2. So that's 2.4 times 10 to the negative 2. And then we are multiplying this by 2 times 2. And then we are dividing by 2 times 10 to the negative 3. That is 24. So our answer is going to be the square root of 24, which is 4.9. Square root of 24. So we know that v squared equals 24. So v equals the square root of 24, which is 4.9. V equals 4.9. And then finally we have E. What is the speed at point C? Oh boy. So this is a similar problem to what we did in part C, but now we have to do slightly more work. This part over here, this part of the, we have a laser pointer, this part of the equation is exactly the same, except now KEF and PEF is for point C, so our PEF is no longer 0. Now it is, so we know that the right side of the equation is still 2.4 times 10 to the negative 2. But now it equals KEF plus whatever PEF is at point C. PEF at point C is MGH, so it's, let's just put it over here right in the calculator. Let's just do 2 times 10 to the negative 3 times 9.8 times 0.8 for our new height. So that is we'll call it 1.6 times 10 to the negative 2. 1.6 times 10 to the negative 2. So that means KEF equals 2.4 times 10 to the negative 2 minus 1.6 times 10 to the negative 2. So let's do 2.4 times 10 to the negative 2 minus our answer. So our answer is, it looks like it's 8 times 10 to the negative 3. So if 8 times 10 to the negative 3 is our KEF, so if KEF equals 8 times 10 to the negative 3, then we can solve for v squared the same way we did before. We're going to take our answer, multiply it by 2, divide by 2 times 10 to the negative 3, and then take the square root of our answer. And our final speed is v equals 2.9 meters per second. That is, in fact, the correct answer. Finally, what is the total mechanical energy of the bead? Well, this is really straightforward. The total mechanical energy is the kinetic energy plus the potential energy at any point. We already calculated that several times. We can see over here that the kinetic energy plus the potential energy at point A is the same as the kinetic energy plus the potential energy at point B. And in fact, it is just 2.4 times 10 to the negative 2. That was a long question. In the figure, a ball hangs by a very light string. What is the minimum speed of the ball at the bottom of the swing in order for it to reach point A, which is 1 meter above the bottom of the swing? So basically, we need to know how much kinetic energy do we need to increase the potential energy by 1 meter. So in order to increase the potential energy by 1 meter, that means that we need to increase mgh joules. We don't know what m is, but as we're going to see, we're not going to need it. So the potential energy that we need to add is equal to m times 9.8 times 1, which is just equal to whatever m is, times 9.8. So how much kinetic energy is m times, how much speed do we need in order to have m times 9.8 joules of energy? So Ke equals 1/2 mv squared. So in order to have m times 9.8 joules of energy, our speed needs to be 1/2 mv squared. We have an m on both sides of the equation, so it's going to cross out. So you can very clearly see that in order to have the same amount of kinetic energy as the potential energy that we're going to need, we multiply both sides by 2. We end up with 19.6 equals v squared. Take the square root of both sides, and we end up with a final speed with an initial speed of 4.4, which is the correct answer. Square root of 19.6 is 4.4. 19.6, 4.4 is the correct answer. You want to store 800 joules of energy in an ideal spring, which is compressed only about 1.5 centimeters. What should be the spring constant of the spring? The amount of potential energy in a spring equals, we'll call it PE, is 1/2 kx squared. And you're told that x is 1.5 centimeters, which is 0.015 meters. So PE needs to equal 800 equals 1/2 k times 0.015 squared. Solve for k. Multiply both sides by 2, you get 1600. 800 times 2 divided by 0.015 squared is going to be that monstrosity of a number. It appears to be 7.1 times 10 to the 6th. And that is the correct answer, 7.1 times 10 to the 6th. 7.1 times 10 to the 6th. Whatever the unit is for ideal springs, it's joules over Newton over meters, doesn't matter. A 15-kilogram car is moving at a speed of 25 meters per second, hits an initially uncompressed horizontal ideal spring with a spring constant of 2 times 10 to the 6th. What is the maximum distance the spring compresses? I believe this question was on your homework, so I'm not going to go over it. Assuming that the bricks are lifted with a constant speed, what is the minimum power of the motor that runs a lift must produce to lift a load of bricks weighing 900 newtons to a height of 9 meters in 22.2 seconds? So power equals work over time. We are given the amount of time. So all we need to do is calculate the work. How much work is required to lift a load of bricks weighing 900 newtons to a height of 9 meters? Well, we have to figure out what their change in potential energy is going to be. So initially, the potential energy is going to be 0 because it's on the ground. You're lifting it 9 meters, so that means that the final potential energy is PE equals mgh. This is a tricky problem because they do not give you m, they give you the weight, which is mg. So weight equals mg. So instead of substituting in 900 for m, you substitute it in for mg. So you end up with just the PE being 900 times 9. And that gives you 8,100. So that is the change in potential energy, and as a result, it is the total work. So as a result, the power is going to be 8,100 divided by 22.2. And the answer is going to be 8,100 divided by 22.2 is 364.86 watts. We're going to call that 365 watts. And that is the answer. Power is 365 watts of power. Moving on. Let's see. How many more of these do we have? All right, 5 more. We could do this. Find the magnitude of the impulse delivered to a soccer ball when the player kicks it with a force of 1,100 newtons. Assume the player's foot is in contact with the ball for 3 times 10 to the negative 3 seconds. Impulse equals F times delta T. F is 1100. Delta T is 3 times 10 to the negative 3. Just multiply these two together. And you get 1100 times 3 times 10 to the negative 3 is 3.3. I is 3.3. The unit for impulse, I imagine, is the same for momentum. So that's kilogram. Something. Oh, Newton seconds? We're going to go with Newton seconds. Okay, well, you live and you learn. 0.5 kilogram ball is initially at rest on the grass. When the ball is struck by a mallet, the average force exerted on it is 150 newtons. If the ball's speed after being struck is 5 meters per second, how long was the mallet in contact with the ball? So we're using the same equation. I equals F times delta T, but they do not give us anything about I. So instead, we need to use I equals F times delta T, which also equals the change in momentum, which is delta P. Initially, the momentum is 0 because the mass is 0.5, and initially the velocity equals 0. But afterwards, the velocity is now 5. So that means the change in momentum is 0.5 times 5, which is 2.5 minus 0. So that's just 2.5. So the change in momentum is 2.5 momentum units. So that means that F times delta T also has to equal 2.5. And we know that F equals 150. So 2.5 equals 150 times delta T. We can see delta T. We can see that delta T is going to equal 2.5 times divided by 150, which makes a lot of sense. Generally speaking, when things are hit, they are in contact with that thing for a very short amount of time. 2.5 divided by 150 is 1.6 times 10 to the negative 2. Yeah, that's what we're going to go with. 1.6 times 10 to the negative 2. I believe your answer sheet is given in milliseconds, so just roll with it. We're going to go with 1.6 times 10 to the negative 2 seconds, or 1.6 millisecond, or 16.7 milliseconds. Same difference. I don't really care. Two canoes are touching at rest on a lake. Can I just do that? Is that helpful? Yeah, sure. The occupants push away from each other in opposite directions, giving the canoe 1 a speed of 0.8 meters per second, canoe 2 a speed of 2 meters per second. If the mass of canoe 1 is 400 kilograms, what is the mass of canoe 2? This is a conservation of momentum problem. Whatever the momentum of the two canoes was before the collision needs to be the same combined momentum as the two canoes after the collision. The combined momentum of the two canoes before the collision is 0 because they are both at rest. So that means 0 needs to equal M1 VF1 plus M2 VF2. Now, the only way this works is if one of these quantities is negative, which makes sense because they're going in opposite directions. So that obviously means one of the canoes is moving in the negative direction. We are going to arbitrarily decide that canoe 1 is moving in the positive direction, which means that we have the mass of canoe 1 times its final velocity, which is 400 times positive 0.8 plus M2 times negative 0.2, and then all we need to do, and all of this equals 0, so then all we need to do is solve for M2. 400 times 0.8 is going to be like 3,600 or something like that. Close. 320. 320 plus negative 0.2 M2 equals 0, which means that that 320 equals 0.2 M2. Divide both sides by 0.2, and we get the mass of canoe 2 is 1,600 kilograms. 1,600 kilograms. Again, this answer makes sense. Canoe 1 is significantly lighter, so it's going to be moving faster. When a light thing and a heavy thing push off each other, the light, like if you push off a wall, for example, you are going to move much faster than the wall is going to move away from you. Makes a lot of sense. A cart of mass of 2 kilograms moves with a speed of 0.6 meters per second on a frictionless air track and collides with an identical car that is stationary. The carts stick together after the collision. Find the initial kinetic energy of the system and the final kinetic energy of the system. Let's do the easier one first. The initial kinetic energy of the system is relatively straightforward. Initially, the second cart isn't moving. It is stationary, so that means all of the kinetic energy comes from cart number 1, which is just 1/2 times 0.2 times 0.6 squared. Let's go over to our calculator and do 0.5 times 0.2 times 0.6 squared, and we get 0.36. For some reason, it's giving me because I forgot a point there. So it's 0.036. Apologies for that. So it's 0.036. That is the correct answer. The final kinetic energy of the system, so the two carts are sticking together and they're moving at the same speed. We need to know how fast they're moving. The only way for us to know how fast they're moving is to use the law of conservation of momentum. Pi total needs to equal Pf total, which means that M1v1 plus M2v2 needs to equal M1v1 plus M2v2, where this is V1 initial, this is V2 initial, this is V1 final, and this is V2 final. So, as we established, the cart number 2 not moving initially, so therefore all of this momentum equals 0. This is just 0.2 times 0.6. So go away. 0.2 times 0.6 is 0.12. Oh, and I made a mistake over here. Since the two carts stick together, we can treat them as just one giant object. So all of the momentum is just m1 plus m2 times vf, because they have the same velocity. So this equals m1 plus m2. Cart 2 is identical to cart 1, so that means they weigh the same. So 0.2 plus 0.2 is just 0.4. So this equals 0.4 vf. So we have 0.12 equals 0.4 vf. Our final speed of the two carts is going to be 0.12 divided by 0.4. 0.12 divided by 0.4, so that's 0.3. Vf equals 0.3. So what is the final kinetic energy of the system? Final kinetic energy of the system is 1/2 0.4 times 0.3 squared. Again, that's 1/2 mv squared. So now we do 1/2 times 0.4. We do 0.5 times 0.4 times 0.3 squared. And we end up with 0.018. That is our final 0.018. That is our final kinetic energy. You can see that we have lost half of the total kinetic energy in the system. We began at 0.036 and we ended at 0.018. That makes sense because this is an inelastic collision. Similarly, we have a similar problem. 2 kilogram object traveling east at 20 meters per second collides with a 3 kilogram object traveling west at 10 meters per second. After the collision, the 2 kilogram object has a velocity of 5 meters per second to the west. How much kinetic energy was lost during the collision? So first, let's calculate the total kinetic energy. Then we will calculate the speed of object number 2 because we don't know it. And then we will proceed to calculate the kinetic energy after the system and compare the two quantities. So Ke initial equals 1/2. Let's draw that neater. 1/2 times 2 times 20 squared. We're going to just arbitrarily call east positive and west negative. Plus 1/2 times 3 times 10, negative 10, but it doesn't matter, squared. And you plug all this into a calculator and you get 0.5 times 2 times 20 squared equals 400 plus 0.5 times 3 times 10, negative 10 squared. But again, like I said, it doesn't really matter. Negative 10 squared is 150. 400 plus 150 is 550. So the total kinetic energy initially is 550. In order to find the kinetic energy afterwards, we need to figure out how fast cart number 2 is going. The way we do that is the way we did it before. Momentum beforehand plus equals the momentum afterwards. So 2 times 20 plus 3 times negative 10. Stop it. Equals, after the collision, cart number 1 is moving to the west. So now that's negative. So this is negative over here. So we have 2 times negative 5 equals 3. Plus 3 times VF for the cart that we care about. Again, so the total momentum beforehand, mass times velocity, plus mass times velocity has to equal mass times velocity, mass times velocity. So this is 40, this is negative 30. 40 plus negative 30 has to equal negative 10 plus 3VF. So this is 10 equals negative 10 plus 3VF. Plus 10 plus 10 gives you 20 equals 3VF. VF is 20 divided by 3, which is 0.667. We're going to call it 6.67. I'll just do it over here. 20 divided by 3 is 6.67 meters per second. So that means that the total kinetic energy afterwards is, so this is M1, this is V1, this is M2, and this down over here is, M1, V1, M2, V2. So the total kinetic energy is 1/2 2 times negative 5 squared plus 1/2 times 3 times 6.67 squared. And all of that is going to equal the following. 0.5 times 2 times 25 is 25. This is going to be much less. Lost a lot of energy in this collision. Plus 1, here, let's do 0.5. 0.5 plus 3. Oh, not plus 3. 0.5 times 3 times 6.67 squared is going to be 91.7. We'll call it 91.7. So how much kinetic energy was lost in the collision? So initially we had 550 joules of energy. Then we ended up with 91.7. The difference between those is 550 minus the answer. 458 is our delta KE. Our delta KE is negative 458. That is how many joules we lost in the collision. Thank you for coming to this extended presentation.